Okay, so we talked about that we are dealing with the real number line, the set of real numbers, and we looked at the natural numbers, which are also called the counting numbers, the whole numbers, which are the counting numbers plus 0, and the integers, which are all the negatives and positive whole numbers plus 0, and then you've got your rational numbers, which can be written as a fraction with an integer numerator and denominator, where the denominator is not 0. And then the irrational numbers, which are numbers that cannot be written as a ratio of integers. That's why rational numbers are called rational, because there's a ratio of integers is what makes a rational number. Irrational numbers cannot be written as a ratio of integers. All right, so the real numbers are the irrational numbers plus the rational numbers. So that makes up all the real numbers. And then the rational numbers are your integers, whole numbers, and your natural numbers. All right, a quick question. Can my calculator always give me the exact answer? Not always, because decimal answers can't always give you the whole story when you're dealing with an irrational number, because it will never end and it never repeats in a pattern, so there's no way the calculator can show you what it really is exactly. Remember, mathematical modeling is basically changing words or situations into mathematical formulas, equations, expressions, and graphs. So if we wanted to give 4 mathematical models that express the set of all numbers greater than or equal to -4 and less than 2.3, we could do that with a graph. So we could look at all the numbers greater than -4 and less than 2.3, and that would be those numbers between the two. And in this problem, it wants greater than or equal to -4, so we put a bracket to say that we're including -4, and we put a parenthesis on 2.3 to say we only want the numbers less than 2.3, not including 2.3. Another way to talk about this set of numbers would be with set notation. We would say the set, where you use curly brackets, of all x such that x is greater than or equal to -4 and less than 2.3. So that would be the set notation for this group of numbers. And then interval notation is just 2 numbers in parentheses or brackets telling you where you're starting at -4 and where you're going to 2.3. You're including all the numbers in between. And in this case, you include the -4, but not the 2.3. Okay, so here's another situation where you might want a mathematical model. It says the maximum recommended heart rate, M, for adults is the difference of 220 and the person's age. So we want to write a model, a mathematical model, to represent that maximum recommended heart rate. So we say, it says that it's a difference, so that means minus. It's the difference between 220 and the person's age, and we know the 220 is going to come first because that's the greater number, and we want a heart rate that's positive. I don't think there's such a thing as a negative heart rate, so we're good with this equation for the mathematical model for those words. All right, finding the union and intersection of sets. When you find an intersection, which is what you find when you have this upside down U, then you're finding the numbers that two sets have in common. First of all, they give us these sets. D is the set of all numbers less than 4. E is all the numbers greater than or equal to -2. And F is all the numbers less than or equal to -3. So first of all, if we just go ahead and graph those sets, it kind of gives us an idea in picture form of what we're talking about there. Then we want to find D intersect E. So there's D on that number line and E on this number line, and you can kind of see where they have numbers in common. It's from -2 up to 4, but not including the 4. And then set notation for that would be D intersect E is equal to the set of all x such that x is between -2 and 4, but x is greater than or equal to -2 and less than 4. And then for the interval notation, it's going to be -2 to 4 with a bracket on the -2 side because we're including -2. Yeah, greater than or equal to -2. Okay. All right, now we want to do D union E. And in that case, you've got all these numbers for D and all these numbers for E. And you can see that if you're going to join those two sets together and say tell me all the numbers that are in D, in E, in both of them. It doesn't matter. Just tell me all of it. You can see that it's going to be every single number on the number line, because all the numbers less than 4 and all the numbers greater than -2, if you're including everything, which is what union is, then that's all the numbers on the number line. So we would just put the whole arrow both ways. And then for set notation, we would say D union E is just the real numbers. And we would say for interval notation, -infinity to infinity. And remember, you have to use regular parentheses for that because you can't get to either one of them. So you would never use a square bracket. All right, E intersect F. If you've got E, it is from -2 up, x greater than or equal to -2. And then for F, you have x less than or equal to -3. So it's those numbers over there. And when you're talking about intersection in this problem, intersection, remember, means the things that the two sets have in common. And in this case, those sets don't have anything in common because one is greater than -2, one is less than or equal to -3. So they don't have any numbers in common. So their intersection is going to be the empty set, which you can represent by 2 brackets with nothing in them, or with this 0 with a line through it. Both of those mean the empty set. But please don't write the brackets and the circle with a line through it, because that's not really good notation. All right, the properties of real numbers, we talked about this. Addition and multiplication are both commutative over the real numbers, which means that you can do the operation in either way. One doesn't matter which one's first, doesn't matter which one's second. They give you the same answer. Associative property of addition and multiplication for the real numbers says saying when you have 3 numbers that you're adding together or multiplying together, it doesn't matter which 2 you do first. And then the distributive property, which says that if you multiply a number by a sum, you can distribute that multiplication. So you can multiply your number by the first addend and then add that to the number multiplied by the second addend. Properties of identity. The additive identity is 0. We talked about that. It is called that because when you add 0 to any other number, it does not lose its identity. That number stays the way it is. With multiplication, the identity is 1 because any number times 1 is that number. And so it doesn't lose its identity. And then for the inverse property, there is an additive inverse. Every number has an additive inverse that will give you the additive identity. So if you have a number A, its additive inverse is -A, or the opposite of A, because when you add those 2 numbers together, you get 0, which is the additive identity. Multiplication has, and each number has an inverse, a multiplicative inverse, which is also called its reciprocal, where if you have a number A, inverse, is called 1 over A, and A times 1 over A gives you the multiplicative identity, which is 1. Okay, so absolute value means the distance from 0. If you think about 0 as being home, any number, when you say absolute value of a number, you just want to know how far from home you are. You don't care which direction. So if you are talking about distance, that means it's going to be a positive number. And so if we talk about the absolute value of -6, we just look at where -6 is. How far is it from home? It's 6 away. So that is going to be the absolute value of -6 would just be 6. And then for +3, the absolute value of +3, again, it's only 3 away from home. It doesn't matter which direction. Absolute value of 3 is 3 because it's 3 away from home. All right, so you need a little bit more specific definition when you are dealing with algebraic expressions inside of an absolute value, because you have to be able to manipulate those things. If x is a real number, the absolute value of x is equal to x if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. So we talked about the fact that if you have some stuff inside the absolute value sign, then if that stuff is positive or 0, then the absolute value of that stuff is just going to be that stuff, because it's not going to, the absolute value sign isn't really going to do anything to it because it's a positive number, and the absolute value of a positive number is just that number. Absolute value of 3 is 3. Absolute value of 5 is 5. Anything positive, the absolute value is just going to be the number itself. All right, but if the stuff inside that absolute value sign is negative, then the absolute value is going to be the opposite of the stuff that's inside that absolute value sign. And if you're just dealing with plain old numbers, it's not hard to figure out absolute value. But if you're dealing with variables and algebraic expressions, that's when you have to realize that this situation, this definition is there to help you get rid of that absolute value sign so you can do some algebraic manipulation on whatever it is you have. All right, so we talked about absolute value of square root of 3 minus 3. We said, what is the sign on this stuff? Is square root of 3 minus 3 positive or is it negative? And we said it's negative because we know square root of 3 is less than 3, so square root of 3 minus 3 is going to be a negative number. If you're not sure, you can punch it into your calculator and see what it is, if it's positive or negative. So what we said is that if this is a negative number, then the absolute value of that negative number is going to be the opposite of the thing. So the absolute value of square root of 3 minus 3, because square root of 3 minus 3 is negative, its absolute value is the opposite of square root of 3 minus 3. So we distribute that negative sign and we get negative square root of 3 plus 3. And then just for notation's sake, we would write the bigger number first, 3 minus square root of 3. For the absolute value of 3 minus the square root of 3, we have a positive value. 3 minus square root of 3 is positive. So the absolute value of it is just itself. All right, here we have another one where we want to write this as simply as possible. The absolute value of x minus 4 over x minus 4. It's tempting to want to just cancel that x minus 4 with the bottom, but you can't do that. You have to get rid of that absolute value sign before you can do any algebraic manipulation on this problem. So you'll have to look at x minus 4 outside the absolute value sign, and you'll have to say, is that positive or negative? Well, there's no way to know that except they tell us that x is less than 4. So if x is less than 4, then x minus 4 is negative. So we know that's a negative quantity, therefore its absolute value is the opposite of that stuff, x minus 4. So the absolute value of x minus 4 is negative or opposite of x minus 4. So we can put that into the problem now, and then the absolute value is gone, and we can just simplify this. We have the opposite of x minus 4 over x minus 4, and anytime you have the opposite of a number over itself, you have a negative 1. Okay, the distance between 2 points is just going to be the absolute value of their difference. It doesn't matter which order you put them in. You just subtract the two numbers and take the absolute value. All right, don't forget how to simplify algebraic expressions. When I use the word expression, by the way, I mean something that does not have an equal sign. If you have an equation, that means it has an equal sign, then you're allowed to use all kinds of rules of algebra to simplify it by adding something to both sides or subtracting something from both sides or whatever. But when you have an expression, that's a thing that does not have an equal sign in it, and you can only use certain tools with it. And one of those is just knowing your order of operations. Please excuse my dear Aunt Sally. Make sure you know that you do parentheses first, then exponents, multiplication and division next, addition and subtraction after that. And by the way, super, super important rule of math that can get you into a lot of trouble: don't ever divide by 0. You cannot have a denominator that has a value of 0. So 5 over 0 equals n. That can't happen, because what that equation means is that n times 0 is 5. I mean, if you multiply both sides by 0, you get n times 0 equals 5, and nothing times 0 can be 5. Anything times 0 is 0. So we would say that something over 0 is an undefined quantity, all right? Which is harder, addition or multiplication. Sometimes adding is way harder than multiplying because you can only add like to like. So you might have heard people say you can't add apples and oranges, and this is what they mean. 2 apples plus 3 apples is 5 apples, and 2 oranges plus 3 oranges is 5 oranges, but what's 2 apples plus 3 oranges? You can't add two things that are different and get just a number. You could say 5 pieces of fruit, of course, but that's taking the analogy too far. That's not what we're trying to express. We're just saying that if you want to add two numbers together and get a number, a sum, then you have to be adding the same thing to the same thing. And that's what happens when you're dealing with algebraic expressions like this. When you're adding and subtracting, you can only add what we call like terms. First of all, you need to know that terms are separated by addition and subtraction. So this expression right here has 5 terms. So in order to know what a term is, you have to look for an addition sign or a subtraction sign. Don't break terms apart by where there's multiplication. That's not where they break. They break between addition signs and subtraction signs. So that one right there has 5 terms. Well, let's look at another one. We have this that has 5 terms, and let's look at which terms are like terms. Like terms are going to have the exact same letters with the exact same exponents. So in this particular one, we've got 2 terms that have just ax squared. So they're like terms. 5ax squared minus 2ax squared is 3ax squared. Also, we have 2 terms that have a xy. That's the only, that they have the same 2 letters with the same 2 exponents. So 3xy plus 2xy is 5xy. And then we have 7ax cubed y squared, which doesn't have any other terms like it. So we can't do really anything with that. Note, you can multiply without having to worry about this kind of thing. ABCD times EFGH is just ABCDEFGH. It is easy to multiply variables. Adding is hard because you have to look for like terms. You can only add like terms. All right, reminder about raising something to the 0 power. If you have a number that is not 0 and you raise it to the 0 power, you will get 1. Anything to the 0 power is 1, but you have to make sure about what you are actually raising to the 0 power when you have an expression. So we'll look at that again in just a second at the bottom, but we're also going to talk about negative exponents. Remember that a negative exponent tells you to flip the base. In other words, take the reciprocal of the base and then raise it to the opposite sign on that exponent. So b to the negative n is the same as 1 over b to the n. 4 to the negative 1 is the same as 1 over 4 to the first, positive 1. X to the negative 3 is the same thing as 1 over x to the positive 3. Back to raising something to the 0 power, you've got 6y to the 0 power here. And when you look at this, you have to realize that that 0 is only affecting the y. It doesn't affect the 6. The only way to show that it would affect the 6 would be to put the 6 and the y in parentheses and then put the 0 power on the outside of the parentheses, like in the second situation here. So 6y to the 0, the first situation, is 6 times y to the 0. So 6 times 1 is 6. The second one, those parentheses are showing me that I want the whole thing raised to the 0 power. So 6y, the whole thing raised to the 0 power, is 1. And then on the right, you've got negative 5 to the 0 power. There are no parentheses here. And so really only the 5 is being raised to the 0 power. The negative, which kind of represents a negative 1 being multiplied by the 5, is not being affected by the 0. In order to have the whole thing to the 0 power, you'd have to put the negative 5 in parentheses and put the 0 on the outside. So the negative is not affected, and we just have negative 5 to the 0, or negative 1. All right, let's just look at a few examples here about the properties of exponents. You know probably that when you multiply like bases, you add the exponents. When you divide like bases, you subtract the exponents. All those properties of exponents are on page 21 if you need to look them up. But I'm pretty sure that you've used them enough now to know them. So let's just run through a few examples where we use them. So in this problem, 13 to the 0 power is 1. And then we're going to flip those bases and change the sign on the exponents. You've got 1/3, all of that raised to the negative 2 power. So that is equal to the reciprocal of 1/3, which is 3 over 1 squared. So the positive 2 power. And then 1 over 9 to the negative 1 power is 9 over 1 to the positive 1 power. So when you take the reciprocal of the base, you change the sign on the exponent. So this is 1 plus 3 squared, which is 9, plus 9 to the first, which is 9, which is 1 plus 9 plus 9, which is 19. Okay, we have all this stuff in parentheses raised to the negative 2 power. First of all, if you want to get a positive exponent here, you can just flip the fraction upside down and change the sign on the exponent. So I'm changing it from 14a squared b to the 7th over 2a to the 5th b, all raised to the negative 2 power, to 2a to the 5th b over 14a squared b to the 7th to the positive 2 power. So I'm flipping the base upside down and raising it, changing the sign on the exponent. Now I'm going to distribute the exponent. So I'm going to distribute that 2 to everything in the numerator. 2 squared, a to the 5th squared, b squared. And I'm going to also distribute it to all the things in the denominator. 14 squared, a squared squared, b to the 7th squared. So everything gets squared. Okay, so now you just go through and use your rules for exponents. 2 squared is 4. A to the 5th squared, you multiply the exponents, so it's a to the 10th. You've got b squared on the bottom. 14 squared is 196. A squared squared, you multiply 2 times 2, so it's a to the 4th. And then you've got b to the 7th squared, so 7 times 2 is 14, so b to the 14th. And now, since you are, you have a fraction where you're dividing the bases, you can subtract the exponents. So you would have, first of all, simplify 4 over 196, which is 1/49th. And then A, you've got 10 minus 4, which is 6. And then B, you've got 2 minus 14, which is negative 12. You could write that as a to the 6, b to the negative 12. Or if you want to, you could just put that b to the 12th, b to the negative 12 in the denominator and call it b to the positive 12th. Either one of those answers is fine. It just depends on if the question asks you to leave it a certain way. But either one of those would be correct if you weren't asked to put it in a certain way. But it is as simplified as it can get. Don't lose your parentheses because we have to make sure we're raising that negative 3x to that exponent, the whole thing, negative 3x, not just the x or the 3, but the whole thing. And so now we can distribute our exponents. Oh, I was saying that again. Don't forget that you don't change the sign on the base. You only change the sign on the exponent. So negative 3x to the negative 4 is not 1 over positive 3x to the positive 4. It's 1 over negative 3x to the positive 4. You change the sign on the exponent, not on the base, because you know that negative 3 is not the same thing as 1 over 3. Okay, so we're going to distribute the 3 to all the factors inside the parentheses there. So for the numerator, we'll have 4 to the 3rd, x to the negative 6, because 3 times negative 2 is negative 6, and then y to the 3 times 3, which is 9. And then in the denominator, we've got negative 3x to the 4th power, so we're multiplying negative 3x by itself 4 times. I'm just writing that out so you'll see you won't lose sight of exactly what you're doing there and why you get a positive answer. So you've got 64x to the negative 6, y to the 9th, over 81, x to the 4th. And you can subtract negative 6 minus 4 and get negative 10 for the exponent on x. And you can put that in the denominator like this, where you'll have a positive 10 on the exponent in the denominator. Or you could have put it in the numerator and had a negative 10 on the x. But either way would be acceptable. Okay, so reminders about scientific notation. I think I put this in your notes incorrectly. There was a typo. Scientific notation is in the form a times 10 to the n power, where a is between 0 and 10, not 0 and 1. I think it might say between 0 and 1 in your notes. So a is supposed to be between 0 and 10, meaning that this number that you're multiplying the 10 to the something by, that number has to be between 0 and 10, meaning that there can only be one digit to the left of the decimal place, or it's not in scientific notation. Remember that if you're talking about a tiny number, you're going to have a negative exponent, because if you have something like 0.000000345, you're going to be writing that as 3.45 times 10 to the negative 7, because you're saying, if I have the number 3.45, I want to move the decimal 7 places to the left to get the number I'm talking about, which is this tiny number, 0.0000345. So when you use a negative exponent on 10, you're expressing a tiny number. And that's the purpose of scientific notation, is to express tiny or gigantic numbers, so you don't have to write a bunch of zeros. All right, and if you have a big positive If you have a big number like 35 million, you're going to have a positive exponent because that's going to be 3.5 times 10 to the 7th. So 3.5, but I don't want the decimal by, to the left of the 5. I want it way over there after 6 zeros. So I'm expressing where that decimal really belongs. So right here, it's, that decimal is not where it should be for 35 million. All right, so when I say 3.5 times 10 to the 7th, I'm saying 3.5, but hey, wait a second. I want that decimal to be way over here because I want this to be a big 35 million. So that's scientific notation. We'll just do a little practice problem here. A light year is the distance that light travels in 1 year. If light travels at a speed of 6.7 times 10 to the 8 miles per hour, how far will it travel in 1 year? And if they're telling us that 1 year is 8.76 times 10 to the 3rd hours. That's a lot of hours. And so remember, first of all, to do this problem, rate times time equals distance. And rate, in this case, the speed of light is 6.7 times 10 to the 8 miles per hour. The time is a year, which is 8.76 times 10 to the 3rd hours. And that's going to give us our distance. All right, so you would multiply 6.7 times 8.76, and you will add the exponents on the tens, because when you have like bases, you add the exponents. So 10 to the 8th times 10 to the 3rd is 10 to the 11th. Now you multiply the decimals, and you're going to have 58.692 times 10 to the 11th, but that's not done. That's not in scientific notation because 58.692 is not between 0 and 10. We said there can only be one digit to the left of the decimal, so we have to rewrite it, 5.8692 times 10 to the 1st, that's the 58.692, times 10 to the 11th, and when you add those exponents, you get 5.8692 times 10 to the 12th miles. That is how far light travels in a year. Okay, what does square root mean? For a greater than or equal to 0, the square root of a equals b if b squared equals a. So the square root is the number you multiply by itself to get that number. So the square root of a is the number that you multiply by itself to get a. Square root of a times square root of a is a. Square root of 4 times square root of 4 is 4. Square root of 29 times square root of 29 is 29. Square root of 3y squared a to the 4th times square root of 3y squared a to the 4th is 3y squared a to the 4th. My point is that it's the number you multiply by itself to get whatever that number is that's under the radical. Okay, so there's one little tricky part to this when you're solving algebraic equations, which you're going to be doing, polynomial equations, quadratic equations. Sometimes when you take the square root on both sides of an equation, you don't just mean, well, you mean something different than this radical sign, this little check mark looking thing. That's called the radical sign, and it is reserved for expressing the positive square root of a number. So all numbers actually have two square roots. So a positive square root and a negative square root, because of course 4, if you want to know what number you can multiply by itself to get 4, you could either multiply 2 by itself, 2 times 2, or you could multiply negative 2 by itself, negative 2 times negative 2, and you would still get 4. So 2 is a square root of 4, and negative 2 is also a square root of 4. But when you see the radical sign like this, where it's just square root of 4, that means just positive 2. It's just the notation means 2, not negative 2. It never means negative 2. But sometimes when you're solving an equation like this and you take the square root on both sides, you will end up with a positive 2 and a negative 2, even if you might use that symbol. But whenever you see that symbol in a book or elsewhere, it only means the positive square root. Nth root. For a positive integer n greater than or equal to 0, the principal nth root of a, denoted by nth root of a, is a number b such that nth root of a equals b means that b to the n is equal to a. The nth root of a number is the number you multiply by itself n times to get that number. So if n is even, a and b have to be greater than or equal to 0. So first of all, we'll look at fifth root of 32. That means the number you multiply by itself 5 times to get 32, and that number is going to be 2. 2 times 2 times 2 times 2 times 2, 5 of them, is 32. That's what a fifth root means. The number you multiply by itself 5 times to get 32. Now, the cube root of negative -0.008. That means the number you would multiply by itself 3 times to get -0.008. The cube root of -0.008 would be -2/10, because 0.2 times -0.2 times -0.2 is -0.008. You can punch it in your calculator and find out. Notice this is a negative number under the radical sign. That's okay as long as this index here is odd. In the case of the fourth root of -1, you've got a negative number under the radical, but this is a even number. So you can't have this. There is no real number that has a fourth root of -1. There's no number you can multiply by itself 4 times to get -1. So that's not a real number. The opposite of the fourth root of 1 is the opposite of just 1, because 1 is its own root. So -1. Fourth root of 1 is 1, and you have a negative sign in front of it, and so that's what you get. Rational exponents. Fractional exponents. When you see the word rational, it usually has something to do with fractions, because fractions, sometimes you think of them as what we call a ratio. All right, so when you have a rational exponent like a to the 1 over n, it deals with roots. A to the 1 over n means the nth root of a. A to the m over n means the nth root of a raised to the m power. So when you have a rational exponent, the numerator of it means the power, and the denominator means the root. So 25 to the 1/2 means you're going to take the square root of 25, and we know that's 5. The 64 over 27 to the 1/3 means take the cube root of 64 and the cube root of 27. So you'll have 4 over 3, because 4 times 4 times 4 is 64, and 3 times 3 times 3 is 27. So 4 is the cube root of 64, and 3 is the cube root of 27. You got -81 to the 1/4. That means the number you can multiply by itself 4 times to get -81. And we just said that you can't, if the root, which in this case is 4, is even, you can't get a negative number, because an even number of factors will always give you something positive. So this is not a real number. There is no number that is the fourth root of -81. There's no real number that's the fourth root of -81. Okay, then you got 32 to the 3/5. This means you're going to take the fifth root of 32, which we just talked about, which is 2, and you're going to raise it to the third power. So the fifth root of 32 raised to the third power is going to be 2 to the third power, which is 8. Now you have -27 to the 2/3 power. That means you're going to take the cube root of -27 and square it. So you take the cube root of -27 and you're going to square it. So cube root of -27 is -3, because -3 times -3 times -3 is -27. And when you square that, you're going to get 9. Don't lose your parentheses. Make sure you're doing that power to all the things inside the parentheses when that power is outside the parentheses. Okay, now we have some fractional exponents that are on variables. So we just can use what we know about exponents when you add them, when you subtract them, those kinds of things. When you multiply like bases, even if they're letters, you add the exponents. When you divide like bases, you subtract the exponents. So in this first one, we're going to have x to the 4/7, x to the 2/7, and x to the -1/7. If you bring that x to the 1/7, flip it up to the top, it becomes x to the -1/7. And now we just add all the exponents together because they're all like bases. They all have an x in the base. It's just plain x. So x to the 4/7 plus 2/7 minus 1/7 is going to be x to the 6/7. Over here we have another situation kind of like this. All these exponents are positive, so we don't have to worry about flipping anything, but we can go ahead and distribute the power that's outside the parentheses to all the factors inside the parentheses. So on the first one, we've got squared, so we're going to have, sorry about that, 5 squared, c to the 3/4 squared, over d to the 1/2 squared. So all the things in that first fraction were squared. Then in the second fraction, everything's got to be cubed. So d to the 5/3 cubed, and 2 cubed, and c to the 1/2 cubed. Everything got cubed. All right, so when you raise a power to another power, you multiply. Don't multiply 5 times 2. It's 5 squared, which is 25. So 25 c to the 6/4 d to the 5th, because when you multiply 5/3 by 3, you get 5. And then in the denominator, you've got d to the 1/2 times 2, which is just d to the 1. Then you've got 2 cubed, which is 8. And then you've got c to the 1/2 raised to the 3rd, which is c to the 3/2. Now we can subtract the exponents on the c's and subtract the exponent on the d's because they're like bases. Don't subtract the 25 and the 8. They are not exponents. They are bases. Leave them alone. So you would have c raised to the 6/4 minus 3/2 and d raised to the 5 minus 1. And so you would end up with 25c to the 0 d to the 4th over 8. So that c to the 0 is just 1. So 25 times 1 is 25. D to the 4th over 8. Simplifying radicals. It's important to make sure that anytime you write a radical, whatever kind of root it is, that it is as simplified as it can get. And what I mean by that is that a simplified radical has a radicand, that's the stuff inside the radical sign, that has no factor other than 1 that is a perfect nth power. That's going to make sense in a minute. No fractions can appear in the radicand. You can never have a fraction inside the radical sign. No denominator of a fraction may contain a radical, so no radicals in the denominator of any fraction, ever. And the exponents in the radicand may not all share a common factor with the index. So here we have the cube root of c to the 5th. Let's look at the rules here. It says a simplified radical has a radicand that has no factor other than 1 that is a perfect nth power. That's not true here because c to the 5th can actually be factored to c cubed times c squared. C cubed is a perfect third power. The cube root of c cubed is just c. All right, so this was not simplified yet. It had a perfect cube in it, so we have to factor that out, and then the perfect cube, c to the 3rd, can escape from the radical. And this is what we're talking about in rule 4 here. The exponent on any factor under the radical can't share a common factor with the index. In this case, they share a common factor of 3. So we got to get that c cubed out of there because it is a perfect cube. So this would be c cube root of c squared. So the c cubed was able to escape because it's c times c times c. Cube root of c times cube root of c times cube root of c is c. That's what cube root means. It's the number you multiply by itself 3 times to get, in this case, c. So the c escaped. The c squared is still in there. And that's as simple as this one gets. Okay, if we wanted to reduce the square root of 50, now we're dealing with square roots, something you've probably dealt with longer than cube roots and other kinds of roots. One of the ways you've probably done this for a long time is if you look at a number and you know a perfect square that's in that number, that's a factor of that number, you can just factor it out. So you might want to say square root of 50 is equal to the square root of 25 times 2. And since you know the square root of 25 is 5, you can just take that square root of 25 times square root of 2, and you just have 5 square root of 2. Another way, if you have a number and you don't know that there's a perfect square factor, you're not sure, one way you can do it is just to write the prime factorization of whatever is inside that square root or cube root or whatever kind of root it is. So for a square root, and this is a pretty simple prime factorization for 50, it's just 2 times 5 times 5. And in this case, you see that you have square root of 5 times square root of 5, which according to the definition of square root is 5. So 5 square root of 2. Either way is fine. You may have to use this second way a lot more once you start dealing with numbers that you're not sure if there's a perfect square or not. When you have something like this where you have some variables and a number and all these things, and you're trying to simplify the radical, which is a 4th root, now you've got to deal with all these issues. You're trying to get out all the perfect 4th roots. It's one of the things you have to do. So you can look for things that are perfect 4th roots, things that can be rescued from the radical. They can escape because they are raised to the fourth power. So because if you take the fourth root of something raised to the fourth power, they cancel each other out and you just get whatever that base is. So 32 you can write as 2 to the fourth times 2 to the first. X to the ninth can be x to the fourth times x to the fourth times x. And y to the sixth can be written as y to the fourth times y squared. And so the 2 to the fourth, the x to the fourth, the other x to the fourth, and the y to the fourth are all perfect fourth powers. So if you take the fourth root of those numbers, you will just get those numbers themselves, 2, x, x, and y. And the other things are left inside. So when you add those exponents on the things on the outside, you get 2x squared y, and then you've got the fourth root of 2xy squared. All right, here you've got a square root of x cubed over 9. Again, you want to see if you can find some perfect squares in there. So you've got x cubed can be written as x squared times x, and we already know that the square root of 9 is 3. So we can get that x squared out. It becomes just x because the square root of x squared is x. And then the other x stays in, and then you've got the 3 on the bottom. So in this next one, you have the cube root of 3x to the 7th y over the cube root of 81xy to the 4th. And the fact is that the quotient of two radicals is equal to the radical of the two quotients. In other words, you can rewrite this as the cube root of that quotient, of that fraction. Fraction means division, quotient. All right, so you can just take the cube root of that whole big fraction, and before you try to do that, you might as well simplify the fraction, because you know that 3 goes into 81, and you can subtract the exponents on the x's and y's, and then you can deal with the cube root part. So it would be the cube root of the 3 and the 81 cancel, so you'd have 27 on the bottom, and then 7 minus 1 for the powers on x gives you x to the 6th. And then for the y, you have 1 minus 4, which is negative 3, and you can put that y to the third in the denominator since it has a negative exponent and make that exponent positive. When you take a cube root, it's the same as raising whatever that is to the 1/3 power. So that's another way you could think about it, and you could distribute that 1/3 to all the powers you have now. So x to the 6th raised to the 1/3 is x to the 6th. X to the 6th times 1/3, which is x squared. And 27 to the 1/3 is 3. Don't divide 27 by 3. Raise 27 to the 1/3 power. And then y cubed to the 1/3 is y to the 3 times 1/3, which is y to the first. Now we're going to multiply some square roots. You can, if you are multiplying two square roots, it's the same thing as taking the square root of the product. So you can have the square root of 60, and then you can do the prime factorization if you want to, if you didn't know that 4 was a factor of 60, which you may have done. So you know that that's 2 squared times 15. The 2 squared is a perfect square, 4. Square root of 4 is 2, so you can take that out, and the 15 stays inside the radical. Okay, so for this next one, you have really 4 factors here. You have 2 times the 4th root of x cubed, times 5 times the 4th root of x to the 7th. Now remember that multiplication is commutative over the real numbers, so it doesn't matter what order you multiply these things in. You can multiply the 2 times the 5 first, and then you can multiply the 4th root of x cubed times the 4th root of x to the 7th. And since those are both 4th roots, if you're multiplying two 4th roots together, you don't have to, you can do the multiplication inside the 4th root. So the 4th root of x cubed times the 4th root of x to the 7th is the 4th root of x cubed times x to the 7th. And then you can add the exponents on those x's because they're like bases. So 2 times 5 is 10, and then you'll have the 4th root of x to the 10th. And then you'll remember that you don't want any perfect 4th roots in there. So we can remember that's going to be 10 times the 4th root of x to the 4th times x to the 4th times x squared. That's x to the 10th. So the x to the 4th can come out. The other x to the 4th can come out. The x squared has to stay in. So the 4th root of x to the 4th is x, and the 4th root of x to the 4th is x. And so you would have 10 times x times the 4th root of x squared, and that would just be 10x squared, 4th root of x squared. I know I'm showing a lot of steps that you probably wouldn't show, but I'm just trying to make sure you understand exactly what's happening, and I wouldn't expect you to show every single one of those steps unless you needed to get the right answer, which if you do, you should do them. Okay, this other one, you have 5 cube root of 7t squared minus 2 cube root of 7t squared plus 1 cube root of 7t squared. So all these terms you have here, you've got 5 of that stuff, 2 of that same stuff, and 1 of that stuff. That stuff is the cube root of 7t squared. So these are like terms, meaning I can add them all together as cube root of 7t squared. So I've got 5 of them, I've got minus 2 of them, and I've got 1 of them. It's going to give me 4 of them. Another way you can think of it is that you're factoring out the cube root of 7t squared from each term because they all have that factor. So cube root of 7t squared times 5 minus 2 plus 1, which is 4. Cube root of 7t squared. So like terms can be combined. All right, again, in this next one, you have some like terms. You have 3 square root of 5x, and you have 2x square root of 5x. So you can think of it as factoring out the square root of 5x, and that would be the square root of 5x times 3 of them plus 2x of them. And the one on the right, you have what looks like not like terms, but actually they end up being like terms. This can be simplified a whole lot. And there are a few ways you can do it, which is the case with a lot of these problems. The way I'm showing you right now, it may not be the only way to do it, and you may do it a different way. You may think it through in a different way. As long as it's the correct way, you're fine. As long as you're following the rules for exponents and roots and all those rules that are in your book that you've probably already learned in Algebra 2. You should have learned in Algebra 2. Okay, so on this one, you can start out by looking at what's inside the square root sign. You can see 98 has a perfect square factor of 49. 49 times 2 is 98. So we can factor that. And then x cubed has a perfect square because it's x squared times x. And then y does not have a perfect square, so it's just sitting there. And then in the second radical, 18 is 9 times 2. 9 is a perfect square. And then x to the 5th can be written as x to the 4th x. X to the 4th is a perfect square. And then you've got a y, which is not a perfect square. So you're going to go through and take out all the perfect squares that can get out of the radical. So on that first radical, you can take out the square root of 49, which is 7. And you can take out the square root of x squared, which is x, but you're multiplying it by the x that's already on the outside, so you get x squared. And then what's left is the square root of 2xy. And then on the right, you take out the square root of 9, which is 3, and multiply that by 5 to get 15. And you take out the square root of x to the 4th, which is x squared. And you're left with the square root of 2xy in the radical. So you can see that both of these terms have a factor of x squared, square root of 2xy. And you have 7 of them in the first term, and you have 15 of them in the second term. So 7 plus 15 is 22. You have 22 of those things. Apples, oranges, x squared, square root of 2xy. And that's your homework. And if you have any questions, please email me. Have a good week, and I'll see you next week.